Welcome, math models, to the probability of compound events. We're going to be mainly looking at 2 events, but you could do this with 3 or 4 or more events if you wanted to. And we are going to be looking at both some independent and some dependent events, kind of on a basic introductory type level. So if you have 2 events that you're wondering what's the chances of one occurring and then the other one occurring after it, this is how you would go about looking at that. So the probability of event A and event B is the number of ways event A can happen out of the total times the number of ways event B can happen out of the total, and these totals may not be the same total. Something to be aware of. Some events are independent, which means that the outcome of one event does not affect the outcome of the other event. For example, if you have 2 dice during a game, one of them giving you a 6 or something does not influence the other dice unless you're throwing them against each other or doing something weird like that. But in general, they don't affect each other. So, speaking of dice, you roll 2 6-sided dice during a game. If you get a 6 on both, you win an extra turn. What are the odds that you'll win an extra turn? So we're going to get probability of 6 on one and 6 on the other. So just take them kind of one at a time. If you get a 6 on one die, that is 1 choice out of 6 total choices. Don't get into the trap of going 6 out of 6 because it says you get a 6. There's still one way to do that. There's still just 1 6 on the dice. So 1 out of 6. Then times. And then for that second die, it's still just 1 option out of 6 total options. Multiply them together, and you get 1 out of 36. And you can go ahead and convert that to decimal and percent form. But there you go. So they're not great chances of you winning an extra turn, but I don't know, could be worse, I guess. Hey, it's an extra turn, that's cool. Let's look at a few more independent events. So you pick a card from a standard deck, then put it back and draw another card. What is the probability of getting an ace and then getting another ace? So we got our deck again. Let's see if I can get an ace. The probability of getting an ace. That's a jack. Okay, we'll try again. Yeah. All right, ace. Come on, ace. Alright, fine. Let's try again. Yes, finally. And notice what I was doing every time. After I picked a card, I put that card back. So I still had 52 of these beauties to choose from to try to get my dang ace. So, each time, there are 4 aces in the deck. 4 aces in the deck. And 52 total cards in the deck. No matter what I did. So, the first draw, I have 4 aces out of 52 total cards. The second draw, I still have 4 aces in there out of 52 total cards. So those totals are both the same in this case. And then you end up getting 1 out of 169 simplified, which is 0.0059, which is 0.59%. So really not good. Odds, less than 1% chance of this happening. Sad. Let's look at one that's a little bit better. You flip a coin and roll a 6-sided die. What is the probability of getting heads and an even number? So even numbers on a standard die are 2, 4, and 6. So you flip a coin, heads, that's a 1/2 chance. And then times, then this one you got 3 choices out of 6. You could go ahead and write that as 1/2 if you wanted to. Either way, you're going to get 3 out of 12, which is 1/4, which is 0.25, which is a 25% chance, which is super way better than that. Oh my goodness, yay. Woohoo! Okay, so remember, independent events means the two outcomes don't affect each other. Now we're going to look at some where they do affect each other. Sometimes events are dependent, which means the outcome of the first event influences the outcome of the second event. Okay, so now I want you to imagine there's a bag with some delicious Starburst. And there's 20 red Starburst, 15 pink Starburst, 22 of those nasty yellow ones, and 28 of the nasty orange ones. Your friend chooses one first, and then you choose one. What are the odds of you and your friend both getting a coveted, delicious red Starburst? Well, your friend has 20 red Starburst. Let me write that out. 20. You have 20 reds when your friend chooses out of, that is 85 total. You can just trust me. I'm a doctor. Times, now think about it. Your friend took that red Starburst, they hope, and they're sure as heck not going to give it to you, and they're not going to put it back in that bag, because why would you ever give up a red Starburst if you had one, right? So by the time you get to choose, you only have 19 red ones left out of 84 total Starburst, because your friend took one. So you're going to multiply those together. The denominators did change. We have 19 out of 357 is our, believe it or not, simplified fraction, which is 0.0532, which is about a little over a 5% chance of both of you getting a delicious red Starburst. Don't fight over it. All right, one more. You pick a card from a standard deck, you don't put it back, and then you draw another card. What is the probability of both of them being aces? So let's look at that scenario, shall we? I have my cards, and I really want an ace. Let's see if I can find one. Let's see. Is this an ace? No. Okay. Really? Oh, goodness. No aces. I'm here somewhere. Finally! You know, it'd be interesting to figure out how many cards I'd have to pick on average in order to get the stinking ace. But there's finally an ace. But you know what I didn't do this time? After I picked a card and failed to find an ace, I didn't put the card back. I just left it out. So what happened each time with each successive card? Well, believe it or not, I had a better and better chance of finding an ace each time I didn't pick one, because the total number of cards got smaller. So just something to keep in mind. That's called without replacement if you don't put the item back without replacement. You may want to write that here. This is without replacement. If you see that phrase, that's what I want you to think of. Me going through that deck, trying to find an ace, and failing miserably. Anywho, let's say you actually do find one the first time. There are 4 aces in that deck out of 52 total cards. But if you actually manage to get an ace the first time, which is like my dream, I guess, there are only 3 to choose from the second time out of 51 total cards, because you took one out already. So when you multiply those together and simplify, you get 1 over 221, which is really not great chances at all. In fact, that's actually worse than before, because you managed to get an ace out the first time. Interesting. So in any case, after looking at these notes and following along, hopefully you have an assignment on Schoology. Please let a teacher know if you need any help or if you are confused about any of this at all. And as always, thank you for watching.